page. Those are all examples of systems that might be a little bit easier to pick the elimination method to use as you're tackling the system and trying to solve it. Does anybody remember kind of like what you're looking for if you're going to use the elimination method for systems? Yeah. Yes. Okay. So we're looking for, and now here's my personal recommendation for you because I feel like it makes it easier. I would look for opposite, and I'll show you how to do it. If sometimes teachers will have you add the lines together, sometimes they'll have them subtract. I would always want you to add, just it makes it less room for error, but you want opposite coefficients on the same variable. That's what you're going to look for. And we might have to manipulate to create that for ourselves, but opposite coefficients on the same variable. So like what I mean, like maybe one equation has, I don't know, 3x and the other equation has negative 3x. And then what you do, once you have that, and like I said, we might have to create it, you literally just add the two lines together in your system. So I'm going to write down, add the two lines together. When you do that, if I take a positive 3 and a negative 3, like my tiny little example there, they eliminate each other because they add up to nothing. Okay, now, like I said, some teachers would have you subtract. I would tell you, please add because it's just less room for error. So if I look at this very first system here, I immediately notice both of my x's have a 4 on them. So I'm thinking, okay, that's good. What I would just recommend here, and it doesn't matter which one, you could do it for either one. I am just going to run a negative through one of those equations. I'm just going to do it in the second equation. And what I mean by that, I'm just going to multiply everybody by -1. If I do that, that's going to create a system where my coefficients on the x's here are going to be opposite. So just everybody gets a negative. It's just going to change the sign. So it's going to be -4x minus 2y equals -20. All right. My whole goal here, I'm kind of tackling the x. You could tackle the y too, but it's a little bit less work maybe to go after the x here. So when I add 4 and -4, eliminated and gone. Then you just combine like terms. So positive y minus 2y, this would be minus 1y or just minus y. 0 and -20 is -20. What's going to happen there, the two negatives are going to cancel out. So y is going to end up being positive 20. Now, unlike substitution, usually when you do elimination, it's not like one equation is easier than the other to plug it back into. I usually maybe pick one of the original equations in the system, but you can plug this back in any equation that we've been using for y. I'll just go ahead and use the first one. So we had 4x plus y. Instead of y, I'm going to substitute in what we figured out y to be equal to, which is 20. That was equal to 0. So all I'm doing, I'm subbing it back into that first equation for y. So I'm going to subtract 20, and then I'm going to divide by 4. So then our x-coordinate is just going to end up being -5. All right, and then if you want to leave it like that, that's fine with me. If we're doing something on the computer, it's going to ask you to write the coordinates of the point of intersection of those two lines, which would be on a graph, the point -5. Is anybody having a question? Okay, so if I look at this next system, you don't have any coefficients that are the same or opposites to start out. The first line is -2x plus 15y equals -32. The second line is -7x plus 5y equals -17. If I was trying to create opposite coefficients on one of the variables so I could get rid of it, can anybody think maybe what they would do for this problem to go about? John, what do you think? Perfect. Okay. Only thing I would tell you there, let me do -3. So that way the one y will be positive and one y will be negative. You're good. Perfect. Okay, I'm just going to copy the top line. And you guys don't have to do this. I just like to rewrite it to the side. Now, just please, please, please be real careful because sometimes people will forget to multiply one of the terms. So make sure everybody gets multiplied by -3 there. So negative 7 times negative 3, we're going to get 21 x's. That'll be positive. Negative 3 times 5, this is what I want. I want my y's to be opposite. So when I get that negative 15 there, that's golden. And then negative 3 times negative 17 is going to turn into a positive 51. Once you're there, we're doing what we set out to do, get rid of one of the variables y here. So when I add the bottom line to the top line, cross those out. Negative 2 and 21 will give you 19 x's. Negative 32 and 51 gives you 19. And so x is just going to end up being 1 there. And again, you can plug that back into any one of the original equations, or you can plug it into that equation we created. It's totally up to you. I usually just use one of the ones from the original system because they usually have better or smaller coefficients. Let's say it that way. So I'm going to do negative 7 times x, but what I'm going to do is I'm going to put 1 in place of the x. Plus 5y equals negative 17. All right, so I got negative 7 plus 5y equals negative 17. I'm just going to add the 7. So I get 5y is equal to negative 10. And then y is just going to end up being negative 2. If you plug that into a different equation, we should still get the same exact answer. So it doesn't matter which one you want to plug it into. And then my answer there is going to be 1, negative 2. That's where those two lines would intersect. Now, these two at the bottom are a little bit trickier. So I'm just going to cover this one up so we're not even looking at it for a moment. What am I going to do here? I've got 2x plus 4y equals negative 4, and I got 3x plus 5y equals negative 3. Perfect. Okay. Why did you pick those? Good. If you can't, like in the original system, we're not multiplying 2 by anything nice to get 3. We're not multiplying 4 by anything nice to get 5. So in that case, we're going to multiply both equations. Now, you could pick the x's or the y's, either one. You just steal the coefficient from the other equation. So if I'm going to get rid of x here, this 2 just comes down here, this 3 just comes up here. Just make one of them negative. It doesn't matter which one, and that'll give you your opposites. Just be real careful that you make sure to multiply everybody by whatever you decided to multiply by. So that top line should become, what, 6x plus 12y equals negative 12. And if I run a negative 2 through that bottom line, it'd be negative 6x. That's going to eliminate our x's. Minus 10y. And then equals positive 6. Negative times a negative is going to give you a positive. I've got opposites on my x's, so those are going to eliminate each other. 12 minus 10 is going to give you 2 y's. Negative 12 plus 6 is going to give you negative 6. So then y there, if I divide by 2, is going to end up being negative 3. And then whichever equation you want to use, you can use either one we just created, or like I was telling you, I usually just use one of the ones in the original system. So I'm going to do 2x plus 4 times negative 3 is equal to negative 4. So I'd get 2x minus 12 equals negative 4. I'm going to add the 12. So that's going to give me 2x is equal to 8. And I'm not writing all my work out, forgive me, I'm just running out of space. And x is going to end up being 4 for that question. Trying to save a little tiny bit of room. So my intersection of those two lovely lines there is going to be 4, negative 3. Okay, now I have one more, and this one is a little rough looking. So I've got a bunch of fractions in this next system. So I've got x minus y over 4 equals negative 1. And then I've got negative x over 5 plus y over 15 equals 1/3. Okay, what I would recommend here for you, you don't have to, but if you don't want to deal with the fractions, I would just try to think of a number that you could multiply either one of the lines just like individually, like something I could multiply by to get rid of the fractions is what I would recommend. So if I just looked at that first equation there, what's something I could multiply by that would get rid of all the fractions in that equation? Let me think. 4. Okay, just grab your denominator. If we just have one denominator, just multiply by 4. Okay, if I do that, what would I write down first? If I go through there and multiply everybody by 4, what would my first term be? 4x, right? Okay, now what would you write in the middle? It would be y. Just keep the minus with it. That y over 4 times 4, the 4's are going to cancel out. What would you write after the equal sign? -4, perfect. Okay, now, got rid of my fractions. This will be way easier to deal with. What would I multiply the second line by to maybe get rid of my fractions and make it easier to deal with? I'm going to try and think of a number all those denominators would go into. 30 would work for sure. Would a smaller number work? What were you thinking? 15 would also work. I'm just going to use the smaller. You can use 30 if you want. It'll work also. I'm just going to use the 15 here. The smaller the number, just the lower the coefficients we're going to have to work with. Because all three of those numbers will go into 30, but they will also go into 15. What? This is very tricky. What would you write as your first term if you multiplied this negative x over 5? What would you write down if you multiplied that by 15? Perfect. Negative 3x. Okay, what would you write down if you had the y over 15 times 15? Plus y. And what about the 1/3? Equals 5. Okay, now, this is super nice for us because after we did that, do you guys notice the y's are already opposites in what we just created? So we can just eliminate right then and there, just gone. And the other part, when we add this together, 4x plus a negative 3x, this will just be x, and then -4 plus 5 will be 1. So that looked really garbagey, but by getting rid of the fractions, it made it not bad at all. Okay, and then here, for sure, I would not recommend plugging that back into the original system, because that would be super annoying. I would plug it into one of these equations we just created in this particular problem to find the y value. So I'm just going to put it into the one right there on the screen. So -3 times x, which is 1, plus y equals 5. So we'd have -3 plus y is 5. Add the 3. Am I still on the screen? Yes, y is going to be 8 there. So it looked really bad to start, but it actually had a nice answer, 1, 8. Is anybody having a question so far? Okay. Now, just like yesterday, I'm going to show you guys what the system's going to look like if we end up with not an intersection, but maybe they have parallel lines, or maybe the two lines actually end up being the same, but it might not be super obvious when you look at the actual system. So the first one on the back, I got -3x plus 5y equals 6. The other equation, I've got 6x minus 10y equals 0. So what would you maybe do to create a situation there where you could eliminate a variable? Top line times 2. Sounds good. All right. Now, I don't even need to introduce a negative here because the x's, if you're looking at them, one's already positive and one's negative, so I don't need to do that. Now, just to save some space, I'm literally just going to write this right underneath the other equation. This would become -6x plus 10y. And then don't forget to multiply the 2 by the 6 also. So this would be 12. So I just left the second equation where it was at, and I wrote 2 times the first equation underneath. So I'm just kind of working, this is my new system, just to save some space. Now, when I do this, the weird part is the x's are opposites, but the y's are also opposites. So both variables get eliminated here. What would you have left on that side of the equation? 0, right? These guys, 6 and -6, 10 and -10, they add up to 0, so it's there. When I do the other side of the equation here, I'm adding 0 and 12, so I'm going to get 12. So if both of your variables get eliminated, you're going to have a special case. What do you think my solution is here? No solution, right? Okay, anytime, you don't have to write not true. I'm just writing this. If this is not true, that's going to tell you there's no solution. 0 is not equal to 12. So that means the two lines must have been parallel. All right. If you guys look at the other system I've got going on here, got -2x plus 3y equals 13 and 4x minus 6y equals -26. What might you do to set up a situation where you could eliminate a variable there. Can't do it right away because I don't have opposite coefficients on any of the same variables. What might I do for that system to create something I can eliminate? Yeah, we'll do top one by 2. Okay. Don't even have to introduce a negative for this one either. We're just going to multiply that guy by 2. Just to save some space, I'm just going to write it right underneath. This will be negative 4x. We'll be able to cross our x's off right away. But what's interesting here, 2 times 3y gives you 6y. The y's are also opposites. 2 times 13 is 26. Okay, now these go, eliminated. The difference here between this and the last problem we just did, negative 26 and 26, those also eliminate each other, but that would be 0. What do you think my solution is in this situation? Yes. Now, this is just my, I sort of could merge this and make it look like an infinity symbol. So anytime you do elimination, if this is the case, you will always get 0 equals 0. So this is true. This is your infinite solutions. It means that those two must have been the exact same line, even though it might not have been really obvious when I looked at it. But it's different than substitution. Substitution, if you get an infinite solutions, you might get something like 4 equals 4 or 10 equals 10. If you're doing elimination, you will always get 0 equals 0 if you have an infinite solution system. Does anybody have a question? Okay, my favorite. Let's do these word problems at the bottom here. All right, this says Mike has a jar of coins in his kitchen with only dimes and quarters. Totally normal to have this. Okay. So I'm just going to let D be the number of dimes, and I'm going to let Q be the number of quarters. And we're going to try and set up a system here. So I've got 2 variables, so I got to have 2 equations or I can't solve for it. So it says Mike's jar of coins has 42 coins in it. So I know that doesn't look like a lot of information, but you can actually write an equation just from that little piece saying it has 42 coins. Then it says separately the value of the coins. So this will be a separate equation. The value of the coins in the jar is $6.45. Okay, if I have 42 coins, that has nothing to do with their monetary value, so like not what they're worth, but if I just have 42 coins and they're only dimes and quarters, does anybody know how you could write an equation to represent the 42 coins? Exactly. Yes, nothing to do with their monetary value, just how many dimes plus how many quarters equals 42. All right, now the other equation, I'm going to say this to you, money goes with money. So if this is $6.45, we want to talk about the value for the dimes and the quarters. So for dimes, every single dime you have is going to be worth 10 cents. So I just put like, you could just put 0.1, you don't need the 0. I just like to do it because it looks more like 10 cents to me. And then every quarter that we have is worth 25 cents. So I'm going to do 0.25 times the number of quarters. And then you just go ahead and set that equal to what they have there is $6.45. Now, to be honest with you, this system, it would be really easy to get one of those equations in that first system or first equation by itself if you liked substitution better. I'm just going to have us use elimination today because that's what our goal is to work on today, is solving with elimination. But the other thing is, this can also be really easy to do with elimination. Anytime you have a coefficient that's just 1, so like I just have 1 dime, 1 quarter here, you just grab one of the coefficients in the second equation, and I'm just going to introduce a negative. So I'm going to go ahead and go after dimes. You could go after quarters, but I'm just going to take this top line and multiply it by negative 0.10. That's going to make my dimes opposites if I do that. You could do negative 0.25 and match up the quarters. It's completely up to you. We should end up with the same answer. So if I run that through there, I'm just going to write it underneath. This would be negative 0.10 times my dimes. Whoops, sorry. Minus 0.10 times my quarters. And then 42 times negative 0.10, it's just going to look like negative $4.20. All right, I'm going to eliminate the dimes. This in the middle is like taking 25 cents minus 10 cents. So this is going to be 0.15 times my number of quarters. And $6.45 minus $4.20 is going to look like $2.25 there. Now remember, if we're doing a question about coins, you can't have part of a dime or part of a quarter. So this should be a nice number. So if it's not, we may have made a mistake. How many quarters am I going to have there? Anybody know? What'd you get? 15. Good deal. Perfect. 15 quarters. Now, for this question, I would definitely tell you one equation is probably way easier than the other to plug this back in to figure out the number of dimes. I would plug it back into that original first equation we jotted down. Or we know we have 42 coins. So if I just do 42 minus 15 of the quarters, we got to have 27 dimes. Now, these would be super easy to check if you want to check. I usually put it into the equation with the money. So I do like 0.10 and I had 27 dimes plus 0.25 times we had 15 quarters, and just make sure real quick that that's $6.45, and it is. So easy to check these if you want to go back and look over your work. Is anybody having a question? Okay, I'll just do one more. Now, this one says, let's see, Hope went to the store. She got 5 apples and 3 bananas for $6.50. And then Grace went to the sink store, got 10 apples and 7 bananas for $13.75. Write and solve a system of equations to determine the cost for 1 apple and 1 banana. Can anybody write me either equation that you would jot down for that system? What do you think? Perfect. 5a plus 3b equals 650. So that equation would represent the girl named Hope. What would you write down for the girl named Grace's equation? Like, what would hers look like based on reading that? Yeah, go ahead. There you go. 10a plus 7b, 13.75. Okay, now A there, it's not the number of apples, it's the price for each apple, and B there is the price for each banana. If I'm trying to do elimination here, what would you maybe do to try to get opposite coefficients on one of those variables? Do I have to multiply both equations, or could I just do one maybe? What were you thinking? Heck yeah, that's what I would do. Get rid of the apples. 5 goes into 10, so just introduce a negative there so we get opposites. This would be negative 10a minus 6b, and what is that? Negative 13. I'm just going to put 0.00 so it's a little bit easier for me to line up and subtract there. Now, the apples are gone. We would have the price for 1 banana, so I don't even have to divide here. 13.75 minus 13 is 75. Now, I'm not describing the number of bananas here. I'm describing the cost. So that means each banana is 75 cents. Completely fine to have a decimal there. Okay, now up to you. I'm just going to plug it back into the very first one. So 5 times my number of apples plus now 3 bananas, but I know they're 75 cents a piece. That was $6.50. I'm just putting it into that very first equation right there. So let me figure out what this is here. All right, I got 5a. If you take 3 times 75 cents, it's going to be $2.25. I'm going to subtract that $2.25 to the other side. So I get 5a equals $4.25, and I just need to take that $4.25 divided by 5. And each apple, if I do that, is going to be worth 85 cents. Totally fine for those to be decimals there. Is anybody having a question? Okay, I have you guys this homework